This is the first time we have been exploring now, begin to explore this new region of space, interstellar space.
Tremendously exciting to think that a spacecraft I had worked on, I had been a part of, was actually now leaving our solar system.
In the late summer of 1977, a slender, gold-trimmed spacecraft sat on the launch pad at Cape Canaveral. Its purpose as ambitious as anything humanity had ever attempted. This was Voyager 1, a machine barely taller than a small car, yet destined to leave the solar system entirely, carrying with it a record of our existence. NASA's vision for this craft was simple in statement: travel to the outer planets, study them in unprecedented detail, and keep going for as long as the hardware would allow. But this was more than simple explorations of distant worlds, because while the original goals were bold enough, what Voyager 1 would eventually encounter went far beyond anything its designers had ever imagined. Engineering and capabilities. Voyager 1's onboard memory, just 69 kilobytes, was smaller than the size of a single email today. Data was stored on a magnetic tape recorder, the same kind of technology once used in 8-track audio cartridges. Every component was chosen for durability, redundancy, and the ability to function without human hands for decades. Its most visible feature was a 12-foot wide high-gain antenna, a white dish that served as its lifeline to Earth. Through this, it spoke to the Deep Space Network, a series of giant radio dishes stationed around the globe. Even at launch, a single message took hours to travel the distance between Earth and the spacecraft. It relied on hydrazine thrusters for subtle changes in its orientation, keeping the antenna locked onto Earth. Its power came from 3 radioisotope thermoelectric generators, RTGs, that converted the heat from decaying plutonium-238 into electricity.
The generator contains a specially produced form of plutonium dioxide. The natural decay of this radioisotope gives off heat, which these thermocouples can turn into electricity.
At launch, they produced enough to run all the spacecraft's systems comfortably. But every year, the power output dropped, and now it has less than 23 watts left, barely enough to light a dim bulb. The instrument suite was designed to observe almost everything it passed: ultraviolet and plasma spectrometers to study atmospheres and charged particles, cosmic ray detectors to measure radiation from distant stars, a magnetometer on a long boom to keep it away from interference, and, of course, its cameras, capable of capturing planetary surfaces in vivid detail. It was, by modern standards, a primitive machine, but it was also a masterpiece of engineering, the kind of craft that could keep going long after its creators stopped speaking about it in the present tense. And in time, it would face challenges no one could have prepared for. Gary Flandreau and the Planetary alignment opportunity. More than a decade before Voyager ever left the ground, a quiet discovery changed the scale of its mission entirely. In 1965, NASA engineer Gary Flandreau, working at the Jet Propulsion Laboratory, was studying the movement of the outer planets when he noticed something rarer: an arrangement of Jupiter, Saturn, Uranus, and Neptune that happened only once every 176 years. It was a cosmic alignment that offered a kind of shortcut through the solar system, a path where the gravity of each giant planet could sling a spacecraft toward the next without using more fuel. In ordinary circumstances, reaching Neptune from Earth would take 3 decades of steady travel. But using this gravity assist technique, the journey could be cut to just 12 years. The spacecraft would essentially fall toward Jupiter, gain speed as it swung past, and then repeat the process at Saturn, Uranus, and finally Neptune, each planet handing it off to the next in a chain of momentum. This was no small adjustment to the mission plan. It reshaped everything. The launch window would be tight, just a few months in the late 1970s, and missing it would mean waiting another lifetime for the same chance. It also meant building not one, but 2 spacecraft, ensuring that the opportunity was used to its fullest. Voyager 1 would focus on Jupiter and Saturn, while Voyager 2 would take the longer, more ambitious path to Uranus and Neptune. The alignment was a gift that couldn't be ignored, and it set the stage for a mission unlike anything attempted before. What lay along that path, however, was more than just planets. There were discoveries waiting that would rewrite our understanding of the solar system itself, major discoveries in the outer planets. Voyager 1's first great leap beyond Earth's neighborhood came in 1979, when it approached Jupiter. The giant world was more than just a swirling ball of storms. Its system of moons turned out to be a miniature solar system of its own. Voyager's cameras revealed volcanic eruptions blasting from Io's surface, the first active volcanoes ever seen beyond Earth. On Europa, smooth, icy plains hinted at a hidden ocean beneath, a tantalizing possibility that life could exist far from the warmth of the sun. The spacecraft also captured the planet's faint ring system, something no one had known existed before. Just 2 years later, Voyager 1 reached Saturn, and the surprises continued. The rings were not solid bands, but intricate, braided structures of countless ice particles shaped by the gravitational pull of tiny, shepherd moons. Titan, Saturn's largest moon, was cloaked in a thick orange haze, an atmosphere denser than Earth's, rich in organic molecules that raised questions about what might be happening on its surface. The images and data transformed Saturn from a distant, mysterious ornament in the night sky into a complex and dynamic world. Voyager 2, on its extended path, would go on to reveal Uranus tipped sideways on its axis, and Neptune with supersonic winds howling across its dark blue atmosphere. Together, the Voyagers expanded humanity's understanding of the outer planets in ways no telescope could match. By the time the planetary encounters ended, the mission had already delivered more than anyone expected. But as the spacecraft moved beyond Neptune's orbit, a new frontier began to unfold, one that would take them to the very edge of the sun's influence. And what waited there was unlike anything the mission planners had predicted. Crossing into interstellar space. Beyond the orbit of Neptune was a vast and turbulent boundary, the heliosphere, a bubble of charged particles and magnetic fields created by the sun. Inside it, the solar wind dominates space. Beyond it, the influence of other stars begins. For decades, scientists wondered where this invisible edge, called the heliopause, truly was. Voyager 1 was destined to find out. As the spacecraft pushed deeper into the outer dark, its instruments recorded a steady drop in the number of charged particles from the sun, while cosmic rays from interstellar space began to rise. These gradual changes hinted that the edge was near, but pinpointing it would take years of patient monitoring. Then, in August 2012, the data shifted dramatically. The solar wind's pressure faded almost entirely, replaced by a denser, cooler plasma that could only come from beyond the sun's reach. Voyager 1 had crossed the heliopause, becoming the first human-made object to enter interstellar space. The achievement was more than symbolic. It gave scientists their first direct measurements of the interstellar medium, the thin, ghostly material between the stars, and confirmed theories that had only been modeled from afar. When Voyager 2 made its own crossing in 2018, it confirmed the pattern, showing that the heliopause was not a perfectly smooth shell, but a shifting, irregular boundary. Now, both spacecraft were traveling through a realm untouched by anything from Earth, their signals carrying the story of a journey farther than any before them. And along with the science, Voyager carried something else into this uncharted territory, a message meant for any intelligence that might one day find it. Symbolism and the golden record. Strapped to the side of Voyager 1 was something that had nothing to do with measuring plasma waves or magnetic fields. It was a time capsule, a gold-plated copper disc known simply as the golden record. Designed under the guidance of Carl Sagan and a small team, it carried 115 images and a collection of sounds from Earth, greetings in 55 languages, music from cultures around the world, the sound of rain, ocean waves, and a mother's heartbeat. Its purpose was not to send instructions or blueprints, but an introduction, a portrait of what it meant to be human in the late 20th century. The cover of the record bore diagrams showing how to play it, the position of our sun relative to 14 pulsars, and the transition frequency of hydrogen atoms serving as a universal cosmic clock. Everything was etched with the hope that, if found by another intelligence, it could be decoded and understood without a shared language. For the mission scientists, the golden record was more than a romantic gesture. It was a statement of permanence, that even if Voyager's instruments fell silent, it would still carry a piece of humanity into the galaxy for billions of years. It might never be heard, it might never be found, but if it was, it would speak for all of us. What no one could have imagined was that decades later, far beyond the last planet, something out there might respond. Ongoing operations and power decline. By the time Voyager 1 crossed into interstellar space, it was already running on borrowed time. Its power came from 3 radioisotope thermoelectric generators, and with each year, the heat from their plutonium cores faded a little more. To keep the spacecraft alive, engineers at NASA's Jet Propulsion Laboratory began making hard choices, shutting down instruments one by one to conserve power for the systems that mattered most. The cameras had gone dark decades earlier, after their planetary flybys ended, but other instruments continued to return valuable data: the magnetometer, cosmic ray detectors, and plasma wave sensors. Even so, the electrical budget was shrinking to the point where, within a few years, only the most essential components, the communication system, and perhaps a single instrument, could be kept running. Complicating matters was the sheer distance. At more than 23 billion kilometers from Earth, a single radio command took over 20 hours to arrive and another 20 hours for a reply to return. Every adjustment, every test, had to be planned days in advance. Repairs were impossible. Only careful reprogramming and creative use of aging hardware kept the spacecraft functional. Voyager 1 was still doing science, still sending back whispers from the edge of the sun's influence, but the margin for survival was thinner than ever. And in 2022, an unexpected failure threatened to end that mission far sooner than anyone had feared. The 2022 data glitch. In May 2022, the flow of data from Voyager 1 suddenly stopped making sense. The spacecraft was still sending signals back to Earth, but its telemetry, the vital information about its position, orientation, and health, had become scrambled, like a voice speaking in a language no one could understand. Even more puzzling, the scientific instruments continued to operate normally. The data wasn't corrupted in transit. Something inside Voyager had gone wrong. Engineers quickly traced the problem to the AACS, the Attitude, Articulation, and Control System, the part of the spacecraft that keeps its high-gain antenna locked on Earth. For reasons they couldn't explain, the AACS had started routing its status reports through a computer that hadn't worked in decades. The result was nonsense data reaching Earth, even though the system itself seemed to be functioning correctly. The real fear was that the antenna might drift off target, breaking the fragile communication link forever. With Voyager 1 so far away, there was no way to physically repair the system. Instead, engineers had to send a carefully crafted set of commands, knowing each one would take 20 hours to arrive and 20 hours for the response to return. Weeks of careful troubleshooting finally paid off. The AACS was persuaded to resume sending its reports through the correct computer, restoring normal telemetry. But the incident was a stark reminder. Voyager was still operational, but it was an aging survivor, and each new fault could be the one that ended the mission. And then, As if to prove that space still had more surprises in store, Voyager 1 would soon encounter something even stranger. The 2023 orientation shift. The turn no one saw coming. Voyager 1's high-gain antenna eased away from Earth and fixed itself on a patch of sky that looked empty by every chart we had. There were no stars of note, no planets, no marked galaxies, just a quiet field that should have meant nothing. The movement was not a software flicker or a bad reading. Deep space gyros showed a real torque event, a rotation you could measure, precise and clean. No thrusters fired. There was no power surge. Solar pressure did not nudge it. No micrometeoroid struck. Yet the spacecraft turned and held, as if it had chosen a target and refused to drift. The direction lined up with a theoretical null zone, a place where pulls cancel and the math goes flat. A thing written about but never seen. The antenna stayed locked, steady and sure, like a listener settling into a chair. And in that stillness, something began to answer in a way no one expected. First, detection of the 3000 Hz signal. It started as the faintest whisper, buried in the data stream from the plasma wave subsystem. A single, steady tone, locked at 3000 Hz, coming from the exact direction where Voyager's antenna now pointed. At first, it could have been dismissed as background noise, the hum of some distant natural process. But this was different. The tone did not waver. It did not fade. It held a precise pitch, as if it were being played, rather than produced by chance. When the data was plotted, a strange order emerged. The tone wasn't just a flat note, it was layered, rhythmic, almost musical. Within its structure were palindromes, patterns that read the same forward and backward, harmonics, branching like overtones on a perfect chord, and embedded deeper still were sequences no random plasma turbulence could form. Prime numbers, recursive patterns, and constants that Voyager's own limited computers could not have generated on their own. The signal was impossibly selective. Its beam was narrow, aimed directly at Voyager 1, not a broad broadcast, not a message spilling into the void. No other spacecraft, no Earth-based observatory, detected anything at that frequency or from that direction. It was as though the source knew where Voyager was, knew how to find it, and knew how to speak in a way that left no doubt the contact was deliberate. What it meant, however, was another matter entirely. 12-hour blackout and data change. For the first time in 46 years, Voyager 1's carrier tone vanished. The spacecraft didn't drift off frequency, didn't fade with distance. It simply stopped talking. For 12 hours, the most distant machine humanity had ever launched was gone from every listening ear on Earth. When the signal finally returned, something was different. The spacecraft's internal clock, the heartbeat that governs every command and every transmission, had been reset, as if the craft had been restarted from the inside, and the data it sent back no longer looked the same. Its packets, once rigid and predictable, now carried structures no one had seen before. New headers, new formats, entire segments that didn't match any of the known systems still operating on board. Engineers checked for faults, for software glitches, for cosmic ray strikes that might explain the change, but nothing fit. The instruments were still functioning. The spacecraft still responded to commands, yet the way it spoke had shifted, as if a new layer had been added to its language. And buried inside that altered stream, there were fragments of something no one could immediately decode. Details that hinted this was only the beginning. Structured reply event. When the altered data from Voyager 1 was finally broken down, something extraordinary emerged. Portions of the 3000 Hz signal had been modified to include altered fragments of the golden record itself, as if the source had listened to its contents and was now sending a reply. The modifications were not random. They were deliberate reworkings of specific images, sound patterns, and encoded diagrams. Among these changes was a subtle shift in the hydrogen spectral line, a universal constant used by scientists as a cosmic reference point. The variation was precise, intentional, and unlike any known natural distortion. Using triangulation of the signal's direction and delay, analysts estimated its origin to be less than half a light-year from Voyager's position. That placed the source deep in interstellar space, yet far closer than any known star. Everything in the signal suggested process, not accident, reception, analysis, and response, as though Voyager's message had been heard and answered in kind. Deeper analysis of the signal. The more scientists worked on decoding the altered transmissions, the stranger they became. The signal was not flat or static, it was layered, with each pass through the data revealing new patterns hidden beneath the surface. These nested structures behaved like an unfolding puzzle, each solution exposing another level. At the deepest levels, the data began to behave in ways that defied standard signal theory. Its patterns appeared to shift subtly, depending on how they were observed or processed, a property eerily similar to quantum systems. Within the most complex layers were three-dimensional geometric forms, structures resembling tesseracts and other hyperdimensional shapes that could not exist in ordinary space. Even more unsettling was the way certain segments of the signal seemed incomplete, as if holding open spaces for data that only humans could supply. It was less like a broadcast and more like an active, evolving conversation, one waiting for a reply. Predictive elements. Further decoding revealed an entirely different class of data embedded within the signal. Ultra-short, high-energy bursts that didn't match any known astronomical events. These packets were timed with an almost surgical precision, appearing at intervals that lined up with no pulsars, quasars, or transient cosmic sources. When mapped against Voyager's path, they suggested a pattern, as though they were marking something ahead. Some analysts proposed they might be predictive, markers pointing toward future cosmic alignments or encounters along Voyager's trajectory. If that were true, it implied not only that the senders had tracked Voyager's course with unerring accuracy, but that they possessed a level of foresight about celestial mechanics beyond even our most advanced models. The bursts were not just noise. They seemed like coordinates in time, meant for someone or something to follow. Possible origins and theories. Theories began to multiply, each more unsettling than the last. Some speculated the source was a dormant alien probe, stationed for millennia at the outer edge of the solar system, awakened only when Voyager's signal passed through its range. Others imagined a signal that had been traveling for eons, crossing interstellar space until, by coincidence or design, it intersected Voyager's path at precisely this moment. Another possibility placed the origin outside our familiar universe altogether, in a parallel dimension or higher reality, bleeding through into our own. Some scientists floated the idea of an ancient detection network, a kind of interstellar tripwire, programmed to react to the first signs of technology crossing a boundary. The comparisons even reached into known mysteries, likening the phenomenon to fast radio bursts, those sudden, unexplained flashes of energy from deep space. Perhaps, some suggested, the signal was part of a much larger beacon network, intelligent in its design, spread across the galaxy like a hidden lattice. Sacred geometry and universal archetypes. Within the visual components of the signal lay patterns that seemed to speak a universal language, forms that had appeared in art, architecture, and nature across countless human cultures. Spirals that followed the golden ratio, interlocking circles forming the vesica piscis, symmetries that mirrored the growth of shells, the spin of galaxies, the branching of trees. The message was not just mathematical, it was aesthetic. It blended art and science in a way that implied the senders believed beauty itself might be a constant, a bridge across entirely different forms of life. The implication was bold, that any intelligence advanced enough to detect and decode the signal would recognize these archetypes, not as random designs, but as shared touchstones in a universe built on the same underlying patterns. The deeper the decoding went, the more it seemed as though the signal was less a transmission and more a mirror, reflecting our own symbols back to us, reframed in a language that spanned the gap between species. Signal recognition threshold theory. One theory began to gain quiet traction among researchers, that humanity had finally crossed a kind of cosmic detection threshold. For over a century, Earth had been bleeding radio, television, and radar into space, a growing bubble of electromagnetic noise expanding at the speed of light. At some point, the signal density would become impossible to miss for any listening intelligence. In this model, Voyager's sudden role was not as the first messenger, but as the catalyst. The craft's golden record and its unique trajectory made it stand out in that expanding wave, a sharp, deliberate note in an otherwise chaotic broadcast. If the senders were watching or listening, Voyager may have been the moment they chose to answer. Predictive convergence. If the signal was deliberate, another unsettling implication followed. The narrow beam precision, the timing of the blackout, and the layered structure all hinted at foreknowledge, as if the senders had known Voyager would arrive in that exact stretch of space decades before it did. How they could possess that kind of foresight was a question without a comfortable answer. It could mean they had been tracking Voyager from the moment it left Earth. Or it might mean they had a map of space-time detailed enough to predict not just orbits, but the actions of civilizations. Either way, it placed them at a level of awareness far beyond anything humanity had ever encountered. Political and ethical debate. The signal's discovery ignited a debate that quickly moved beyond the scientific community. Around the world, governments, research institutions, and even private organizations split into two distinct camps. The first, often called the silence faction, argued that no reply should be sent at all. They warned against drawing further attention to Earth, pointing out that humanity had no idea who or what was on the other end of the signal. The risk, they said, was not just in being found, but in being misunderstood. The second, known as the response faction, believed that an opportunity like this could not be ignored. They proposed sending a cautious planetary message, one built from mathematics, ethical principles, and an honest acknowledgement of our own uncertainty. The aim would be to open a door without appearing threatening. Both sides feared the same thing in different ways, that the message might be misread, and that once sent, it could never be taken back. Cognitive effects and resonant consciousness theory. As the data poured in, some researchers began reporting something unusual, changes not in the signal, but in themselves. A handful described vivid symbolic dreams that felt unlike anything they had experienced before. Others claimed moments of sudden insight, as if complex problems unraveled in their minds without effort. More than a few spoke of strange synchronicities in their daily lives, patterns and coincidences that seemed to cluster in the days after extended exposure to the signal. These accounts were anecdotal, impossible to measure in any conventional way, but they grew difficult to ignore. Out of them came a theory that bordered on the speculative, that the signal itself might be capable of affecting cognition. If its patterns were tuned not just to instruments, but to the structure of perception itself, then perhaps it wasn't only sending data. Perhaps it was shaping the minds that received it. And so, Voyager 1 continues its slow drift into the dark, a silent emissary carrying the distilled essence of Earth, its sounds, its images, its scientific fingerprint, far beyond the reach of any human hand. Whatever the truth behind the 3000 Hz signal, whether it is a product of rare physics, a coincidence of cosmic scale, or the deliberate act of another intelligence, the result is the same. For a moment, our small world's voice touched something beyond it, and in doing so, it proved that a fragment of human curiosity could cross a gulf of light years and still be heard. Even when Voyager's instruments fall quiet and its systems go dark, it will remain a faint, unchanging point in the void, proof that humanity once reached outward and found the universe listening.